everyone, this is Dr. Ma Abdurrahman. Today I'll go through a very important topic for AS Chemistry, all school boards, that is ionization energy. So to start with, what is ionization energy? So actually from the name, ionization is the removal of one or more electrons from an element. And it goes without saying, we're moving this electron from the outer shell. So if I want to go for definition of first ionization energy, as the name indicates, first ionization energy is the energy required to remove one electron. Okay? And to quantify the amount, we're actually removing one electron, okay, from each atom in 1 mole. Okay, so don't forget, guys, to quantify the amount, we're talking about 1 mole. Okay, so 1 mole of atoms, and this has to be in the physical state of gas. So of 1 mole of atoms in the gaseous state. Okay, and the reason behind this, because we need, in any definition, we really need a standard or to standardize things, right? So you need to we know already we have different physical states like gas, solid, liquid. So we need to standardize the state of these atoms at the gaseous state. We need as well to standardize the quantity as well, right? So the quantity here is you're removing the electrons from 1 mole of the atoms in the gaseous states. With that being said, definition here, guys, usually comes in 2 marks, sometimes 3 in some school boards. So focusing on removing 1 electron is a 1 mark from each atom, of course. Don't forget to write each. So 1 electron from each atom, okay? From 1 mole of the atoms, that's the 2nd mark. In the gaseous state is the 3rd mark. So make sure you avail all 3 marks. In some references, you will find, guys, the definition is you're removing, is that you are removing 1 mole. Sorry, guys. Is that you're removing 1 mole, okay, of electrons. 1 mole of electrons, okay, from 1 mole of atoms in their gaseous state, which is completely fine as well, right? Because when you're removing an electron from each atom in a 1 mole, you're actually moving 1 mole of the electrons, so that's a 1 mark, from 1 mole of the atoms, that the 2nd mark, in the gaseous state is the 3rd mark. Make sure you avail all the 3 marks. Now, the second part I want to highlight today is they may ask you to write down the equation for first ionization energy, and it goes without saying, if I'm removing an electron, let's say from a sodium atom, then it has to be in its gaseous state, as we said. So you're removing 1 electron or 1 mole of electrons from 1 mole of sodium in its gaseous state. And definitely, guys, the product you will get is the sodium plus 1. So you're getting the sodium plus 1, okay, also in the gaseous state. So make sure you write this down properly. Sometimes some students like to just add the 1 mole of the electrons to the product, which is completely fine. So sodium gas would give me the sodium ion plus gas plus the 1 mole of electrons. Both of them are correct. Okay, so both of these formulas are okay and are correct to use. I don't need to remind you, guys, that ionization energy is an endothermic process because you require energy. You require energy, right, to remove electrons. So it is an endothermic process indeed. All right, so equation, how to write the equation, definition, done. The third part here in this video is let's guys discuss the factors affecting ionization energy. And please note, they're not gonna ask you to list them. So why are we learning about them? To use them in application questions. They may ask you to compare why ionization energy is different among two type of elements or two type of atoms. And then you need to use these three factors to justify your answer. All right? So let's then go through them quickly, and then I'll give you examples as we go of how to use these three factors in your answer. Factor number one, nuclear charge. Okay, when I'm talking about nuclear charge, I'm talking about the number of protons. So we all know as the nuclear charge increases, the number of the protons increases, the nuclear charge increases. Okay, and as the nuclear charge increases, the nuclear charge is what holds the electrons, is what holds the electrons. So as more that this charge is, definitely the attraction of the electron will be more. So that the first one, the first factor. The second factor is the number of the electron shells. Okay, let me draw here the second shell with another electron. All right. And then there's a third shell. There's a third shell, okay, with this last electron, which is further away from the nucleus. So the more electron shells, guys, of course, I don't need to remind you that in ionization energy, you're removing the electron in the outer shell here, right? Because the attraction upon this electron is the weakest. Look at the distance. Look at the distance between the outermost electron and the nuclear charge, and the nuclear charge. Okay, so look at the distance here is the most. This is the most further. So the attraction between this electron, this final last electron in the outer shell, and the nucleus, the distance is the furthest. So the attraction is the weakest, right? Since the attraction here is the weakest, then this purple electron would require the least energy to be removed out. So the ionization energy would decrease if you have more shells. Okay, so that's to say, if I already remove this electron in the outer shell, and then I'm intending to remove this yellow electron, definitely the ionization energy for this yellow electron would be more. Okay, so attraction falls off very rapidly with distance as the electrons in the electron shell is closer to the nucleus. That means much more strongly attracted, so the ionization energy is more, and vice versa. Shielding is the third factor. However, in my opinion, I find shielding related to the number of electron shells, because what I mean, guys, really by shielding is the number of the shells, okay, between the nucleus and the electron in the outer shell. If there are more shells, that means this particular electron is farther away from the nucleus, so it requires less energy to be removed. That means ionization energy will go less. So I really find these two factors are related or kind of connected. However, in the exam, make sure you talk about each factor separately, all right? Because sometimes there is a mark on you talk about the shielding part as well. All right, so as the number of electrons between the outer shells and the nucleus increases, the outer electrons feel less attracted, so it's easier to be removed because there is more shielding and the energy required to remove these electrons is less. Okay, something else, or let's talk about the take-home note out of all of this. The higher the ionization energy, meaning there is stronger attraction between the nucleus and the electron in the outer shell, meaning You need more energy to remove this electron out. I hope everything was clear, and I'm gonna do much more applications about this. So let's have this application about first ionization energy, which is the trend, not the YouTube trend or the TikTok trend. This is the trend in chemistry, in ionization energy. Okay, so first ionization energy, we notice, or we can conclude actually, that it's decreasing down a group. Why? If you understood what I just explained, you would be able to justify why does ionization energy decreases down a group. Okay, so let's take group 1 as example. I'm just gonna draw a simple drawing which will make your life so much easy. So I have lithium, group 1, sodium, potassium, and rubidium. That's the nucleus. And then electron in the outer shell. Of course, the outer shell electron lithium lies within the second shell, but I'm not gonna draw the first shell just to make the diagram looks, easier, all right? So for sodium, there is one more shell, see? So the electron is further from the nucleus. For potassium, as you move down the group, of course, we know from the IG, as we move down the group, there is extra shell that is added, right? So for potassium, there is one more extra shell. So the electron is further away from the nucleus. For rubidium, one more shell is added, right? So you see in the rubidium, potassium, sodium, and lithium. So you see in the rubidium, the electron is for the furthest away from the nucleus. So as I go down the group, okay, let's move with this step by step, and then we will conclude the answer without any need to memorize. So as I move down the group, there is extra electron shell. We know this is the IG. Okay, that means electron in the outer shell is further away from the nucleus because the atomic radius is more. What do I mean by atomic radius, guys? Is this distance. This distance, the atomic radius definitely is more since we're having more shells. Okay, that means there is also more shielding, right? Shielding is the amount of the electron shells between the nucleus and the electrons in the outer shell. Definitely more shielding. Distance is more between the nucleus and the electron in the outer shell. That means it goes without saying that the nuclear attraction is less over the outermost electron that I require to remove. Nuclear charge attraction is less. That means definitely energy is less. Energy required to remove this electron is less. And hence, the EI, ionization energy, is less. That's it. No more, no less. So once you understand the factors I discussed previously, you will be able to answer this question, why ionization energy decreases down the group. Please note that this also, guys, provides an evidence for the presence of electron shells. Because if electron shells wasn't present, that means we won't expect the ionization energy to decrease. So having it decreasing down the group, meaning there is actually electron shells present. And why do we really need evidence for that? Because please note that all of these electrons, all of these shells, we can't see I'm talking about a dimension where we can't see with our naked eyes, not even under microscopes. That's why we depend on, coming up with models and evidences to support these models. So that's an evidence supports that electron shells really exist. Why I'm focusing on this point? Because at the A-level questions, they may ask you indirectly how decreasing the ionization energy down the group is a proof or is an evidence for the presence of electron shells. And then you need to go over all of what I explained right now. Okay, as you see, guys, A-level questions are complex. They're not straightforward. You gotta get used to this, and I'm gonna help you and support you all the way up till the exam. One last thing I want to highlight in this point, I hear someone is asking, but as I'm going down the group, the proton number increases, right? We know this. We know that the proton number increases, right? The proton number increases, meaning that the nuclear charge increases as well. That means the attraction to the electron in the outermost layer should be more, right? So there should be more attraction. However, this is also a point I want you to include in your answer whenever they're asking you why first ionization energy decreases down the group. Although there is an increase in the nuclear charge as the proton number increases down the group, however, the effect of the shielding and the extra electron shells, which is the increase in the distance, overrides the effect of the increasing the nuclear charge. As if there are two factors that are actually struggling together against each other. Okay? Who would win? Who would win? Nuclear charge is increasing, so attraction to this electron in the outermost layer is more. However, more shells are added, so the distance is less, so the attraction to this outermost electron should be less. Two factors are struggling together, okay, competing against each other. Who would win? Who would win? The factor of the shielding and having more electron shells. So that's why attraction is less. Attraction between the nucleus and the electron in the outer shell is less. That meaning the ionization energy is also less. I hope this point was clear. A very, very important part to understand. The second part of this video about successive ionization energy, again, just go through the name, successive ionization energy. So basically, I'm removing additional electrons. Okay? So you can remove all the electrons from an atom, leaving only the nucleus. Each time you remove an electron, there is a successive ionization energy. For example, they may ask you about, again, definition and equation, just like how we did with the first ionization energy, but they can ask you for the second ionization energy, so they can ask you to define the second ionization energy or the third ionization energy. That's fine, same idea. Or the fourth, they may ask you for the fourth, to define the fourth ionization energy, and so on. They may ask you for definition, they may ask you for equation. Okay, so let's go through both. So if they're asking you about the second ionization energy, the same thing. It's the energy required to remove one electron from each mole, from each ion of a one mole in its gaseous state. Okay, so second ionization energy, you're removing this electron from the +1 ion. This is something I want to highlight. You're removing the second electron, right, guys? So you're removing that from a +1 ion, an ion that has already lost the first electron, because that's the second ionization energy, right? That's the second ionization energy. So this ion already has lost an electron to form the +1 ion. And then when I'm removing the second electron, it would form the +2 ion. Guys, please don't try to learn this by heart or memorize it. Just try to understand things. This is chemistry. You gotta understand it, all right, so you can excel. That's the only way. That's the only way to deal with chemistry, okay? So for second ionization energy, I'm already removing an electron from each ion of a 1 mole of a +1 ion, because that has already lost an electron, to form a 1 mole of the gaseous +2 ion. If they ask me to write down an equation for second ionization energy, and it's definitely an endothermic reaction, that's why we see the plus here. Okay, so for second ionization energy for oxygen, you gotta use the +1 ion oxygen. Don't forget in the gaseous state. If you forget the state symbol, you will lose a 1 mark. So don't forget in the gaseous state to give the oxygen +2, because it already has lost the second electron, plus the 1 mole of electrons. That's the second ionization energy. What if they're asking you to do an equation for the third ionization energy for oxygen? Let's do this together just to train out. So oxygen -2 definitely, because I'm doing the third ionization energy. So oxygen -2, sorry guys, +2, sorry. So oxygen +2, because it's already lost 2 electrons. And now it's on the way to lose the third electron, so it would form the oxygen +2, 3 electrons lost, gaseous states, +1 mole of electron. And we can do this as well. So +2 gas minus 1 mole of electrons would give me a 1 mole of oxygen ion +3 in the gas state. Both of them are correct. Okay, I hope it's clear. That's a general equation for any ionization energy, for any successive ionization energy, which is xn minus 1 would give me xn plus 1 electron. So if that's the n, the plus n, which is +3, then 2 would be the n minus 1, right? Depending that n equals 3. So that's the n plus 3, okay? And then you start from the n minus 1 plus, n minus 1, 3 minus 1 is 2 plus, and don't forget you're removing a 1 more of electron, or you can just add it to the product as the equation shows here. I hope it's clear. Before we move on to the final part of this video, and I'm not going to say the most important, because every single part of this video is extremely important, and they do ask about each part of this video. So I'm just focusing, guys, on the main points. Successive ionization energies, and how can you use the successive ionization energy to show and predict the shell structure of an atom? Usually this comes as a graph, as you see, a graph relating the number of electrons removed. So here you're removing 1 electron, 2, 3, and so on, to log of the ionization energy. There is a common question why we're using log of the ionization energy, not the ionization energy itself, because the ionization energy comes with a huge number, a very big number, okay? So to minimize this number out, we're using the log, just so that the graph can fit. Otherwise, you won't be able to fit the ionization energy into one paper graph, okay? Now, let's look at this. That's the successive ionization energy of sodium. Here you're removing 1 electron. That's the second ionization energy, removing the second, the third, the fourth, and so on, until you remove the electron number 11. What trend do we see here? Generally, look, guys, there's an increase in the ionization energy or in the successive ionization energy, and this goes with all elements, definitely there will be an increase among the successive ionization energy. Why? If you were with me focusing since the start of the video, you will be able to answer this question. Okay? Because that's the nucleus. Okay, I'm just gonna draw a diagram for sodium. That's the first shell of, that's the first shell. That's the second shell. I will fill them up now with electrons, and that's the third shell. Sodium, okay? So we have 2 electrons in the outer shell, in the first shell, the closest to the nucleus. And then the second shell, we all know from the Ig that sodium has 8 electrons in the second shell. So 1, 2, 3, 4, 5, 6, 7, 8. And then there is the single electron in the third shell. When I'm removing the first electron, first ionization energy, I'm removing this electron, the outermost electron, out of the third shell. You notice that this has the least energy, the least ionization energy. Why? As we said, or as we discussed before, because this electron is the furthest from the nucleus, right? Furthest from the nucleus. So it's easier to remove. Also, guys, when this electron is removed, okay, you're starting to remove the second electron, okay, from an increasingly positive ion. What does that mean? For example, guys, sodium has 11 protons, okay? As you are removing the second electron, electrons now are only 10 electrons, right? Only 10 electrons. Protons are still 11 protons, but only 10 electrons. That means you're removing an electron from an increasingly positive ion. From an increasingly positive ion. The nuclear charge here is still 11 among 10 electrons, right? So the attraction here of the 11 protons among the 10 electrons would be more than the attraction of the 11 protons among 11 electrons. There was 11 electrons before, right? After I remove this the second ionization energy, after I'm removing the second electron, okay, the proton are still 11. Still 11 protons inside the nucleus. This one are untouchable. But how many electrons do I have now left? Only 9. And common sense, the attraction of these 11 protons among the 9 electrons would be definitely more. I think now the point is clear. So that's what they mean by, this is because electrons are being removed from an increasingly positive ion. There's a less repulsion amongst the remaining electrons, so they're held more strongly by the nucleus. I hope it's clear. Plus, the repulsion among the electrons is less. Why the repulsion among the electrons are less? Because there are less electrons. That's it. There's less repulsion amongst the remaining electron, so they're held more strongly because the repulsion is less. Why the repulsion is less? Simply because the number of electrons here are less. So repulsion is less, attraction is more. That means I will require more energy to remove the electron from the second electron and the third electron and so on. That's why we see here a gradual, not really gradual, it's a big, sometimes it's a big increase, guys. But you will notice there are 2 jumps. Please look, there's this jump, there's the second jump over there. There are big jump in ionization energy happens when a new shell is broken into. An electron is being removed from a shell closer to the nucleus. What does this big jump, guys, indicates? This indicates the presence, again, guys, that's another evidence That's another evidence for the presence of shells. So sometimes questions are that complicated. How successive ionization energy can prove for the evidence of shells? Because not only it does increase, also there are jumps. These jumps indicates that you are removing the electrons from a shell that is much closer to the nucleus. So there are shells actually. That's an evidence for the presence of shells. Otherwise there won't be a jump. Please guys get this with me. If all the electrons are removed from the same shell, you won't see two big jumps. These two big jumps meaning that the electrons, you are removing now an electron from a new shell. Okay, and I really feel I want to do this again. So that's the first electron, right? First ionization energy. Look at this. It lies in here. Then there's a jump. Why there's a jump when you're removing the second electron? That's the second electron. I see a big jump. Why do you think there's a big jump? Because this one gone bye-bye, right? So now I'm removing the second electron from a shell that is closer to the nucleus. Closer to the nucleus, remember, means more attraction, so more ionization energy. Okay? And then steady increase for the third, fourth, fifth, sixth, seven, eight, nine, steady increase, and then another jump. What does this jump mean? Okay, I'm just gonna remove them one by one. I remove the second electron, okay, the third, the fourth, the fifth, the sixth, the seventh, the eighth, the ninth. Here I'm expecting a jump because I'm removing this electron from a shell that is really, really, really close to the nucleus. That's why I see a big jump, a big increase. And then see guys, these are the two electrons remaining in the first shell. Once you remove them, we're done. That's why there are a total of 11 electrons removed from sodium. Only 11. Guys, you know why? Because simply sodium has 11 electrons. That's why successive ionization energy here is only 11 electrons. You removed all the electrons leaving the nucleus without any electrons. So we end up removing all of these electrons. I hope the subject of successive ionization energy is clear, because that's also a subject for many questions. All right? So graphs like this can wait, let me remove these. So graphs like this can tell you which group of the periodic table an element belongs to. Just count how many electrons are removed, just like how we did here, okay, before the first jump to find out the group. Does this make sense to everyone? See here, one electron was left, one electron was removed before you see the jump. That means this is an element that contains one electron in the outer shell. So this must be in group 1. That's it. Okay, these graphs also can be used to predict the electronic structure of an element. Working from, don't forget guys, you need to work from right to left. Count how many points there were before each big jump, okay, to find out how many electrons are in each shell, starting with the first. So the graph for sodium has 2 points, 2 jumps, okay? So 2 points on the right. So there are 2 electrons in the first shell, a jump, then 8 electrons, which are the electrons in the second shell, as I explained. Then another jump, and then there's a final electron. So these are the electrons in the first shell. These are the electrons in the second shell. Well, that's the single electron in the third shell. That means this is sodium. It's present in group 3. Sorry guys, group 1, present in group 1 because it has only 1 electron in the outer shell. And it's present in period 3 because see, first shell, second shell, third shell. So it's present in period 3 because, as we know also from the IG, the number of shells representing the period number. This is an info that we already have from the IG. Okay. clear for everyone? I really feel I wanna quickly do some exam questions just to show you how application questions can come on what I explained. I know the class is kind of long, but bear with me with these exam questions. It won't take much time. So we come up out of this class with also a knowledge and about the application questions on this topic, on ionization energy. So this table allows the nuclear charge and first ionization energy for 4 elements. First question, safe and sound, write an equation including one state symbol to represent the first ionization energy of carbon. Very simple, very, very simple. So first ionization energy of carbon, so that's carbon in the gas state, and then carbon is losing an electron, still gas state, plus 1 mole of electrons, and then you get 2 marks. Question B, in these 4 elements, what's the relationship between the nuclear charge and the first ionization energy? We already explained that was the factor number 1. As the nuclear charge increases, the ionization energy will increase. That's it, 1 mark, thank you. Explain why nuclear charge has this effect on the first ionization energy. This is much more deep question. Why do you think when nuclear charge is increasing, ionization energy increasing? Because when nuclear charge is more, there is more attraction among the electrons in the outer shell, right guys? So it's harder to remove the electron. That's why the first ionization energy will be more. That's it. Now let's move to the second question about successive ionization energy application. So this graph shows the successive ionization energy of a certain element. To which group of the periodic table does this element belong? Okay, to know which group, I gotta see how many electrons in the outer shell. For me to know how many electrons in the outer shell, we need to locate the first jump. Why? Because after you're removing the electrons from the outer shell, I'm expecting a jump, right? Because you're removing the electrons from the next shell, which is closer to the nucleus. How many jumps do we see here? Clearly, this is the first jump. I know it's not as big as the second jump, but relatively, if you look, see, there's a jump, relatively big, and then there's a huge, dramatic, big jump over there. So there are 2 jumps. That's the first jump, guys. After we're removing how many electrons? 1, 2, and then 3, we start to see the first jump. That means this element is in group 3. Is found in group 3 because there are 3 electrons in the outer shell. Once they're removed, we started to see the jump. Why does it take more energy to remove each successive electron? 2 marks. So I need to talk definitely about removing an electron. Each time you're removing an electron from an increasingly positive ion, we agreed that the ion would have much more positive charge compared to the number of the electrons left. So that's the first reason. You're removing an electron from an increasingly positive ion, nuclear ion. The second reason is that you have less. So the first reason, you're removing this electron from an increasing positive ion. Okay, so there's more number of protons acting among less number of electrons. That will bring me to the second reason, which is that we have less electrons, right? We have less number of electrons. That means there is less repulsion among these electrons. There is less repulsion among these electrons, and at the same time there is more attraction between these few electrons and the protons in the nucleus. I hope this is clear. Okay. What causes the sudden increase in the ionization energy? The 2 jumps. What causes this? You're removing an electron from a shell that is much more closer to the nucleus. What's the total number of the electron shells, not the total number of electrons? They're asking you, because that's a confusing part. Some students will think if they misread it, what are the total number of electrons, and then they're just gonna mention 13. But no, they're asking about the total number of electron shells. How many shells do we have here? That's the first shell that has 3 electrons. That's the second shell, see steady increase, that has the 8 electrons. And then that's the third shell that has 2 electrons. So there is a 1, 2, 3. So I have 3 electron shells. All of these, sorry guys, so I have 3 electron shells. All right, all of these are, I think I lost my, okay, or almost done anyway. So 3 electron shells that are present in this diagram. All of these guys are all of these are information we can conclude out of this graph on hand. Okay, I hope the topic ionization energy was clear for everyone. Thank you so much, and I'll try to upload some more videos. I've been asked for AS biology as well, so next video will be for AS biology. Looking forward to meet everyone, and follow up my channel if you feel it's beneficial. Thank you so much. See you next time.